Good day, everyone. Welcome to the continuation of my lecture in thermodynamics laboratory. Again, I am Delicana, and you can contact me through my email, which I provided here below if you have questions. So, this is still about the mechanical equivalent of heat, but now we're going to talk about data handling and some of its examples. So, these are the usual formulas that we will use in our lecture. The mechanical equivalent of heat J, Q, and then we have C and W. So this is very important for you to remember for this lecture. And we also have as a guide here. This is actually what we are trying to solve in our experiment. So I just put it here as a guide. The specific heat values, approximate specific heat, and molar heat capacity. That they are being scaled in different measures. So now we have to get our data. So in getting our data, it is important to follow a very good procedure. So in this setup, um, I I come up with this procedure. So measure the initial temperature of water and record this as initial temperature T. Perform the experiment, taking note the mass and the height with which the masses or the mass fall. You can do this with a very good ruler. Do this with 50 repetitions. Record the temperature of water after the experiment as T sub F. And repeat the experiment with 100 repetition following the same procedure. For this setup, the shot tube method, so I also come up with these steps here. Measure the mass of the metal shots and measure the initial temperature of the shots. Record this as T. Quickly invert the tube. Do this for 50 repetitions. Measure the final temperature of the shot and record this as T sub F. Repeat the experiment with 100 and 150 repetition following the same procedure. And what we have noticed is that we always have to measure the initial temperature because the delta T is very crucial in this experiment. So the delta T is very crucial here. And so we have to be meticulous about the initial temperature and the final temperature. So before starting the experiment, so take note of the initial temperature and take note that this different in different types of shots. For example, for the case of our shot tube method. So different kind of shot, different um, initial temperature. And also you have to take a good note for our final temperature. And so this is very crucial because these are the things that we need for us to calculate the change in temperature, the increase in temperature. And and also we have the average distance in meter, 1.03 meters. So this has not changed. This can be readily measured and this is constant. So this is crucial here, and you need to take note that before every start of the experiment, you need to take note the initial temperature, and right after, you have to take a good measure of the final temperature. Um, for our example, so after gathering your data, we are now ready to for our example. So example, if in an overnight for your requirements, you ate two Big Mac, 550 kilogram each, and if you are 75 kilograms, how much height you should displace your body to burn to burn this energy. So a very good culture to solve our problem is to identify the given. So in this case, we have two Big Mac, 550. This is now the big C calorie here times 2, that is equal to 1100 calorie. And so we have to convert that to the amount of heat that is generated by this that is generated by this burger, this Big Mac here, and this is also the work that you need to exert in order to burn this energy. So we have 4.6 times 10 to the power of 6 joules of energy that is provided by two of our Big Macs. So another given here is 75.0 kilograms. And a useful formula to solve our example is now the work that is equal to our potential energy, which is equal to the mass times the gravity, and then the change of height. And the change of height is what we are looking for. This is for us. This is in order for us to solve A. So after playing with the equation, we have come up with this equation. Delta H is equal to the work over the mass times the gravity. And so we have 4.6 times 10 to the power of 6 joule divided by your 75 kilograms multiplied by the acceleration due to gravity, that is 9.8 meter per second squared, um, near the surface of the Earth. So you have to displace 6,300 meter in order for you to burn this energy. But if your body is 20% efficient, then you need to elevate um, 1260 meter. That means if your body uses 80% of that energy for its functioning, so you only need to elevate 1260 meter. And so if you ride in an elevator, so you have to displace 630. This is gonna, yeah, 630 meter up and 630 meter down. That is a trip in the elevator that you need in order to burn 4.6 times 10 to the power of 6 joule of energy if your body is 20% efficient. Next is B, using the same data in the previous example, how much kilogram of water you can boil with that amount of energy, given that initial temperature of water is 25 degrees Celsius. So again, we have to um, find the given, and after finding the given, we have known that delta T is equal to 75 Celsius degree. So we can observe here the actual temperatures, and this is now the change of temperature, which is 75 Celsius degree. And the usual formula that we can use is Q equals mc delta T, m equals Q, and m, this is now the mass of water that we are looking for, is just equal to Q over the specific heat of water times delta T. So that's just 4.6 times 10 to the power of 6 joule over 4,186 joule per kilogram times Celsius degree times the delta T, 75 Celsius degree, and that's equal to 14.7 kilogram of water. So we can boil 14.7 kilogram of water using 4.6 times 10 to the power of 6 joule of energy. Yeah, it's either in the form of heat or you have to work 4.6 times 10 to the power of 6 joule. Next example, a 2.0 gram of lead metal shot initially at 20 degrees Celsius. You have to calculate the amount of heat gained by the metal shots if they increase their temperature by 2 Celsius degree. And B, calculate the number of inversion performed in the activity given that the length of the tube is 0.5 meters. So this in this case it is for the shot tube method. So again, you have to look for the given. We have 2.0 gram of lead metal shots. This is equal to 0.02 kilogram of lead metal shots. Delta T is 2.0 Celsius degree, or it's just equal to 2.0 Kelvin. Degree Celsius is not equal to Kelvin, but if we look for the delta T here, we can see that they actually change at the same rate. So I counted here equal. This is not the change of temperature. Then the length of it, we're given length of the tube L, which is equal to zero point 0.5 meters. We have a known constant here. Uh, this is equal to 130. This is a specific heat capacity of lead, which is denoted by small letter c. This is equal to 130 joule per kilogram times Kelvin. The formulas that is useful for our example is Q equals mc delta T, W equals weight times the length of the tube times the number, the n here is the number of inversion. So in order to solve A, which is the heat gained by the shot, so we have to use this formula Q equals mc delta T. So that is just 0.02 kilogram plus 130 joule per kilogram that times Kelvin times the delta T, which is 2 Kelvin. So this is just 5.2 joule. B, number of inversion performed in the experiment. This is now the formula that we have to use. So we are solving for n. So we play with the equation and we come up with this. And so W is just equal to this Q here. So you have 5.2 divided by 0.196 times 0.5. And we can come up with the number of inversion that is performed in this activity if the delta T is equal to 2 degree Celsius in a PB metal shot is approximately 53 inversions. Now I actually include here like an inverted version of our previous example, the last previous example, because we are actually really calculating for C. But it would be very difficult for me to determine the number of inversion here, given that I was we are not able to do this um, really in a face-to-face experiment. So I have to, as you have noticed here, that I use this is actually the thing that we are solving that we need to solve. But I just use this as a reference for my. I use this as a reference for this example in order for me to calculate the number of inversion that I need here. So in this, and so I will be able to calculate the C that we are looking for now. So we have formula that we want to use here. Wait, I'm just going back here. The given is 2.0 gram lead metal shot is equal to 0.02 kilogram of lead metal shots. And then the same change of temperature, 2.0 Celsius degree or 2.0 Kelvin, then same length of tube. Formulas that we use, QMC delta T, C equals Q divided by M delta T, and our work is equal to weight times uh, the length times the number of immersion. This is equal to Q. And so we have to start with the W here. This is the amount of work that is done in our system. So we know the weight of our metal shots multiplied by the acceleration due to gravity, 7.8 meter per second squared. I did not include all of the units here, but all you need to do is you have to take note that this would boil down into J because that is a unit of our work. So you can do that, or you can put everything. You can put all of the units as long as you can come up with a J here. So that's 0.02 kilogram times 9.8 times 0.5 times this is the 53 inversion. This is dimensionless. And so we have 5.2 joule. So this is after 53 inversion, the shots gain 5.2 joules. And that is just equal to our Q here. And so we can calculate the C, which is equal to Q over the mass of the shots multiplied by the change in the temperature. So that's just equal to 5.2 joule divided by 0.02 kilogram times 2 times the change in temperature here. And what we get is exactly the specific capacity that we have for our blood. So that is equal to 130 joule per kilogram times Kelvin. So that's it, guys, for my report. So the sources for my report. So thank you everyone for listening. I hope that you learned something from me today, and make a bless us all. Keep safe, everyone.